In this video, we'll take a look at curve fitting. In the last video, we looked at increasing and decreasing functions and how to find relative maximum and minimum by using the first derivative. In this video, we're going to take a look at another idea, which is called taking a look at concave up or concave down. So we know that an increasing function, that when you read it from left to right, it's going up. The x is, as x gets larger, y gets larger. But notice there are two ways for a function to bend while they're increasing. So a function can bend this way, or a function can bend this way. Notice when it bends this way, as you're increasing, the slopes actually get higher. Okay? As you're bending this direction, the slopes are getting lower. So they're increasing this direction, increasing this direction. This is called concave up. This is called concave down. So as your function is increasing, the slopes of your lines are also increasing. That's concave up. As your function is increasing, the slopes of your lines are decreasing. That's called concave down. Their slopes are still positive, but it's the rate at which the slopes themselves are changing. So we can look at the same way with decreasing functions. There are two ways for a function to bend while decreasing. The function can bend this direction, where this would be concave up, and this would be concave down. It's what's happening to the slopes as your function is decreasing. Your slopes are always negative. In this case, your slopes are getting steeper, so they're increasing. In this case, your slopes are getting flatter, but they're negative, so that would be concave up. This one, your slopes are negative and they're getting larger, so that's concave down. So the first derivative tells us where a function is increasing or decreasing. So the first derivative of the first derivative will tell us where the tangent line is increasing and where it is decreasing. So for example, your function f is decreasing, and then it's increasing, but for the entire function, it's concave up. Then in the next function, f is increasing, then it's decreasing, but the entire function is concave down. So if you take a look, concave down as x's are positive and concave down as x's are negative, or as your slopes increase and then decrease, these two together are concave down, these two together are concave up. So how do we figure out whether a function is concave up or down? We have to take a look at the second derivative. It tells us the rate at which our slopes are changing. So if we take a look at a graph, where's the following function concave up? The function is concave up until it changes direction right about here. So it's concave up, then the function is concave down until it changes direction again here, and then it's concave up again. Then the points at which concavity changes are called inflection points. So the function is concave up, it looks like, from about negative infinity to about, let's see, negative 1.5. Concave up, and then it's concave up again. It looks like about from 0.5 to infinity. The function looks like it's concave down between negative 1.5 and 0.5. And the inflection points, if we estimate, it looks like at about negative 1.5 that the y value is about negative 10, and at 0.5 possibly 0. It's hard to tell on the graph. So what we're going to do is find exactly. It's called the second derivative test. So if f is a function whose second derivative exists on the interval a to b, if the second derivative is positive, then f is concave up. If the second derivative is negative for all the x in that interval, then f is concave down. So let's take a look at the same example we used for increasing, decreasing, relative max and min. So we have the example, the equation y equals 12x minus x cubed. The first derivative was 12 minus 3x squared. The second derivative is equal to a negative 6x. So when we take the second derivative and set it equal to 0, we get x is equal to 0. So now we have graph 0 on the number line. We want to test points to the left of 0 and to the right of 0 in the second derivative. So if we put in a negative, we get a positive 6. That's positive, so that tells me my graph is concave up. And then when I get to 0, then take and substitute 1, negative 6 times 1, I get a negative 6. That's negative. It tells me my graph is concave down. So the intervals where my graph is concave up is from negative infinity to 0. The interval where my graph is concave down is 0 to infinity. Then the x values, since I go from concave up to concave down, at x equals 0, there's an inflection point. And then to find what the inflection point, the y-coordinate, take x equals 0 and substitute it into the original function. 12 times 0 minus 3 times 0 cubed. I get a y value of 0, so the inflection point is at the coordinate 0, 0. So I still have that function graphed. If you take a look at the graph, there's my inflection point at 0, 0. So my graph is concave up, and then it turns into concave down, and 0, 0 is an inflection point. So looking at another example, we've got a quadratic. You know that the quadratic looks like this. So what the result should be is that my graph is concave down for all values of x. So let's see how that works. So the first derivative was negative 6x plus 6. And then the second derivative, I end up with just a constant, negative 6. So I can't set that equal to 0 and solve. So there are no numbers to plot on the number line. But notice the second derivative is negative always. So it doesn't matter what x is, the second derivative is always negative. So that tells me my graph is always going to be concave down. So it's concave down on the interval from negative infinity to infinity. So that means it also has no inflection points.